So you're going to end up with the limit as n goes to infinity of the next term, so n plus 2, x to the what? N plus 1, all over 2 to the n plus 1 plus n plus 1, right? Yes. And you're multiplying that by 2 to the n plus n over n plus 1 x to the n, right there. So as n goes to infinity, what happens to this? Or is there anything that cancels? Like what could you do here? Well, there's pieces of it you could look at. Let's look at the green piece right here. Let's look at n plus 2 over n plus 1. What is that going to go to? This approaches 1. Do you agree?
Yes.
Correct? And then this ends up x to the n cancels, and what are you left with? X. So let's just simplify what we have. We have the limit as n goes to infinity of x times what? 2 to the n plus n all over what? 2 to the n plus 1 plus n plus 1, like this. Do you have that there? Ooh, exciting. Exciting. So you're really now trying to figure out what happens with this, right? So does the n or the 1, do these really matter, right? How important is that n or this 1? Not so much. What are you really looking at? 2 to the n plus 1. So what is this really going to go to? Anybody want to guess? Yeah, this goes to 1/2 right here. It's 1/2 because it's 2 times greater on the bottom. So what do you end up with? You end up with 1/2 limit as n goes to infinity of x. So what's that going to be? 1/2 x, right? It's going to be 1/2 x. Do you agree with that? And for that to converge, what has to be true? It has to be less than or equal to 1, right? The absolute value of this, right? So what's that mean? 1/2 x has to be less than 1, has to be greater than? So x is between 2 and? So what's the radius? 2. It doesn't ask for the interval, right? It just asks for the radius?
Yes.
If you wanted the interval, the only other thing you need to do is? Check the endpoints. Oh, we're not going to do that now, but let's just answer this one. Does that make sense?
Yes.
So the whole key right there was the fact that the power here, it was 2 to the n and 2 to the n plus 1, so it's 1/2. It's the whole key. Yeah, this same thing, but limit as n goes to infinity of 2 to the n plus 1 plus n plus 1 squared times x to the n plus 1. And what are you dividing that by? 2 to the n plus n squared x to the n. So let's look at this in pieces again. What happens here? Anything cancel? That's gone, and you're left with just what? X. That's correct. So then you're left with limit as n goes to infinity of 2 to the n plus 1 plus n plus 1 squared all over 2 to the n plus n squared times just x, right? So what are the dominant features here? The dominant features continue to be this, right? The n plus 1 and the n squared they go to 1, they neutralize each other for the most part. So what does this whole thing go to right here? That goes to 2. It goes to 2. So you end up with this being the absolute value of 2x. So what's the radius on this one? 1/2. The radius is 1/2. Constant times x, absolute radius is 1/2. 听懂啊？对，很好。我是你的最喜欢的老师。对，好。Okay. So yeah, so you end up with, we'll zoom in a little bit here. So we end up with the limit as n goes to infinity, yay, of x minus 3 to the n plus 1 over n plus 1 times 2 to the n plus 1 times what? N 2 to the n over x minus 3 to the n. Look familiar yet? This is gone. What are you left with here? X minus 3. This right here goes to what? 1, right? And then what are you left with on the denominator? 2. So you end up with 1 over 2x, right? So what's the radius going to be? 1 over 1/2, so it's 2. Did you catch that? That was done really quickly, so I want to make sure we pause here. Are you okay with what happened there? What did
it be x minus 3? 1/2 x minus 3? Or?
Oh, sorry. Okay, yes, you're absolutely right. So the x minus 3, thank you. So it's going to be 1/2 what?
X minus parentheses.
That exactly. Hold on. 1/2 times this, right?
Yeah.
Do you agree with this? Does it change the radius of convergence? No, the 3 moves where the interval is, but does it change the radius of convergence?
No.
So really, if you end up with this, kx plus b, right? what's the radius still going to be equal to? 1 over k. So in this case, the radius is still what? 2, 1 over a half. Because all that minus 3 does is move where the interval is. How? Okay, so let's chat about something you've seen before. Ready? Let's chat about something you've seen before. Let's say you're traveling along, and here's a function f of x, okay? And you go to this point right here where x is equal to a. What's the y value right there? What is that y value right here?
F of A.
F of a. So that point right there is a comma what? F of a. So let's say we didn't know much about this function. Let's say we knew the function, but we were really having a hard time working with it, and we were only interested in the values around, in the neighborhood. It seems like an imprecise word, but neighborhood is actually a word you will use when you take more math, neighborhood. The idea is, if we zoomed in really far here, and we wanted to just look at the values right there, if we zoomed in really, really, really far, eventually it'll start looking like it's a what? If we zoom in, a line. It'll look like a line, right? So one way to estimate the values of the function around that point is to draw a what? What kind of line? Draw a tangent line. So if we draw a tangent line right here, if we draw a tangent line, that's the function that passes through that point that has the same slope at that point, meaning the derivative is equal to, what's the slope going to be equal to of this tangent line? F prime of a. Is everybody okay with that?
Yeah.
So how would you write the equation of that line just in terms of what's on the board? Tomas.
So it'd be 1 minus f of a.
So y minus y. Yeah, so what is this form called?
Point slope.
Point slope is your friend. Stop pushing things into slope intercept unless you absolutely have to. So what do you have here? You have y minus what?
F of a.
F of a equals what?
F prime of a.
Prime of a times
X minus a.
x minus what?
A.
X minus a, right? So if you wanted to write it in slope-intercept form, which the book forces you to do because that's how it writes it, you would have y is equal to f of a, what? Plus f prime of a times x minus a.
It's just sitting there in the period.
Oh, I'm in the wrong one?
Yeah.
Thank you. Let me move that real quick before what could we try to find? We could find the parabola of best fit, and you can game out what this means. So instead of a line of best fit, we could figure out the parabola of what? Best fit. Okay, so before doing a general form of this, let's do a specific example. And the specific example I want to deal with is this one right here. So this one right here. So what do you see right here? What function's in red? What function is in red? Cosine of x, okay? So let's say I wanted to find the tangent line when x is 0. The tangent line when x is 0, what happens to be the slope right there? What's the tangent line slope right there? 0. So it's a horizontal line. So the tangent line is y equals 1. Well, is that very accurate as you get further and further away from cosine?
No.
Not so much. If you were to draw a parabola going downward, does it seem like this parabola right here would be a better model for what's going on?
Yeah.
Absolutely. So we not only want the first derivative to match, we want the second derivative to match. So we're looking for the quadratic that passes through 0, 1, that has the same first derivative, which is 0 in this case, and the same what? Second derivative. So look what I wrote here. What does this represent in blue? What does that represent in blue?
The general equation.
That's any quadratic, right? Do you agree? That's the general quadratic, the general?
Yeah.
And then I took the derivative, and I ended up with 2ax plus b.
Yeah.
I took the derivative again, I got 2a. Are you okay with those two things?
Sure.
Okay, what's the x value we're trying to go through? What's that point right? Sorry, it moved. The x value is 0, and the y value is 1. Are you okay with that?
Yeah.
So we know that the first derivative is going to be, when we're looking at when x is equal to 0. So we take the derivative and plug in 0, and we know what happens when you plug in 0. What are you left with? Just what? B. So the first derivative at 0 will be equal to b. And the second derivative at 0 is going to be have to equal to be 2a. Because is there any x in that?
Yeah,
no, it's always 2a. Are you okay with these three things right here?
Yes.
Okay, so let's look at cosine now. What's cosine of 0?
1.
1. I wrote this out, and there's something I didn't write here. What's cosine prime of what is the derivative of cosine? What's the derivative of cosine?
Negative sine.
What is it? So we're looking at negative sine of 0. What's negative sine of 0? 0. And what's the derivative of sine? So this is negative cosine, right? So what's that going to be?
Negative 1.
Are you okay with your basic trig right here? Are you okay with these three?
Yeah.
So what do you now know? You want the first and the second derivatives to be the same. So what do you know? You know that b has to equal to be what? To 0. And you know that 2a has to equal what? Negative 1. So you know b is equal to c is equal to 1. B is equal to 0 and a, oh, look at that, a is equal to negative a half. So can you now find the coefficients?
Yeah.
So look, there's our a value. What was our a value? Oh, negative a half, right? What was our b value? 0. So what's the invisible thing there? There's actually an invisible 0x, and then what do you add to it? A 1, because what is cosine of 0? It has to go through that point. So what happens when we graph those together? This is what you end up with. What's the blue there?
Cosine.
That's cosine of x, right? What's the red? Negative 1/2 x squared plus 1. So did we make a better model for this function? Yes. So instead of just matching the first and second derivatives, instead of just matching the first derivative, it matches the first and the second derivative. So theoretically, how could we make this estimate even better? What could we do? Instead of a tangent line, we kind of find a tangent parabola. We could find a tangent series. How far could we go? Could we do this for cubic? Could we literally do the same type of work on this? And instead of starting with the general quadratic, could we start with the general cubic?
Sure.
Absolutely. It's not that bad because at least cosine, can you take the derivative of cosine pretty easily? It's cyclical. It's going to keep on repeating, right? Does the algebra get a little annoying? Absolutely. It does get a little annoying. It does get a little annoying. But if you find the cubic of best fit, it'll curve one more time and be a little bit better. And then what about, is there a quartic of best fit? Fifth? So theoretically, how far can we go?
Forever. They just get
Forever. We can go forever. We can go as far as we want. We can go as far as we want. So what are we doing? We are using series to estimate functions. We're using series to estimate functions. And it seems a little weird because cosine of x is such a nice function, right? If we turned it into an infinite series, how many pieces does an infinite series have? An infinite number. That doesn't seem like it's helpful. We're taking something that's very finite, 1, singular, cosine x. And what are we doing? Blowing it up. But if you do that, you suddenly can work with functions you couldn't work with before. So for example, does everybody remember what's on the sign to the Math Resource Center? Everybody remember?
E to
the pi I plus 1
is negative 1. That comes out of, and we're going to do this later, you can take e to the x and turn it into a...
I thought it was 0.
Yeah, I thought it was 0.
Pi 0, sorry. Yes, sorry. 0, yes.
I was like, maybe I'm...
Infinite series. And if you plug in pi I, guess what happens?
Negative 1.
Turns into negative 1. It's really cool. So we're going to get to there, and I'll do all these practical things. So it looks weird. You take something that looks pretty, and then you smash it into a million pieces, and that seems annoying. Those little pieces might cut you up a little bit, but then when you put it back together, sometimes they just like all go away. Really cool things happen. So we need to look at the general form of what this would happen if we did with the cubic, okay? If we did the cubic here, what's the general cubic? I'll just say j of x here. What's the general cubic? Ax cubed plus bx squared plus what? Cx plus d, right? So if I do the first derivative of this, I end up with 3ax squared plus 2bx plus c. Is that correct?
Yes.
J double prime of x, what's that? 3 times 2ax plus what? 2b, in which j triple prime? 3 times 2 times 1 a, right?
Yeah.
Plus 2 times 1 b. I emphatically wrote out the ones because what do you start seeing in there? What do you see? What is that?
Stay there.
The 2 times, sorry, 2 times 1, sorry, thank you. No, it's just gone, sorry. It's just gone, sorry. What do you see right there? What is that? So what are we going to start seeing popping up when we do the general case? Factorials. You're going to see factorials. So for the third derivative here, you end up with a factorial. So I wanted to show you where that comes from. You will see factorials pop up. So the idea here is you want to be able to write a general polynomial. So this right here is the general form for the quadratic. This is the general form for the quadratic one, power 2. What do you end up with? And what's the number? Where is this being fixed? Where are we fixing it? We're fixing it at x equals what? We're fixing it at x equals 0 here. Near 0. Everybody sees that? Theoretically, can you pin these anywhere you want?
Sure.
It just slides like the interval of convergence. You can slide it around. It doesn't change the radius. 0 is just a clean way of doing it. So we're doing this. This means that this function, f of x, is the second order Taylor polynomial. It's f of 0 plus f prime of 0 x. Oh, do you remember how it was 1/2 before? Remember 1/2, everybody? Mm-hmm. There's that too. Anybody want to guess what the next term is going to be? Let's say we wanted P3. If we wanted P3 of x, it's going to be the same thing plus what? Anybody want to guess? F triple prime at 0 over what? 3 factorial x cubed. Oh, that's pretty cool. Ah, exactly. Oh, look at that. So good. Degree 7, we literally have to go to degree 7. We have to go to degree 7. We have to go to degree 7. So what you're going to do in this case, applying what's in this box, our f of x is which function? What is our function we're dealing with? Sine x. Our function is sine x. So how many derivatives are we going to need to take? 7 of them. First derivative, second derivative, third, fourth, fifth, sixth, seventh. Luckily, is this cyclical? Yes. So if you start doing the derivative here, f of x is sine x, and then f prime is cosine, and then you get what? A pattern. So what's the next one here? So what do we get next? I'll draw this in. What's f5 of x? Sine of x. What's f6 of x? No, it's just cosine. Sine is cosine. And then f7 is what? Are you with me so far? Yeah. So then what do you have to plug in for x for each of these? It's around, we wanted it to be around near 0, right? Near 0. So what are we plugging in for x? We're plugging in 0 because we need to determine all of these coefficients. You see these coefficients right here? What does it ask us to do? Yes. Oh, did I skip it? So, that's annoying. I'm really sorry. So what happens to everything downstream? You have to shift it, right? So is it really easy when you're doing these out to skip something? Well, as just proven by your esteemed teacher here, yes. So instead, let's look over here. Oh, look at that. I'm so... It's like I've made that same mistake before. It's amazing. So are you okay with these? Do you agree with these? Yeah. Okay. So there's f of 0, f prime of 0, f double prime. So you're going to have to do this a bunch. I'm not going to ask you to find the 7th derivative of some nasty polynomial unless it goes to 0 really quickly, okay? I'm not going to have to do some product thing like sine, cosine. Find the derivative indefinitely. Be like, no, I'm not going to do that. So what do you do with each of those coefficients? This right here, what is this? That is f of 0, right? And what's that next one? What is this? What's that number right there? F prime of 0. What's this number? F double prime of 0. So do a lot of these cancel out actually? That's f triple prime of 0. And what's this? The 4th derivative at 0. Do you see where those pieces came together? So do a lot of terms just go away? Yeah. What terms go away here? Well, that's gone. This is gone, right? That's gone. This is gone. And what are you left with? You're left with this. Sine x is equal to approximately this for x near 0. It's approximately this. So if could you use this to approximate values around 0? Sure. So if you wanted your approximation, you could do sine of pi over 3 is approximately what? Pi over 3 minus what? The 3rd over 3 factorial plus pi over 3 to the 5th over 5 factorial plus pi over 3 to the 7th over what? And what did I miss there? Minus, plus, and then what? Minus. So theoretically, can you plug that into your calculator and get a value? Absolutely. Absolutely. So what's interesting about this is we just found how to approximate sine around 0 for the 7th degree. How many degrees could we go to? You already answered this. We could go as far as we want, right? What do you think that infinite expansion is going to be for sine based on what you just saw? So if I asked you for sine of x, what do you think the infinite degree or the nth degree Taylor polynomial is going to be? It's going to be all these terms. What do you think the next one's going to be? Plus what? You want to guess? Over minus x to the Exactly. Sine is the odds. You want to guess what cosine is?
Evens.
Something with evens, maybe?
Isn't cosine an even function?
That's just stop it. It's like saying like this is cross product and this is multiplication and this is x marks the spot. Like, yes, those are all true. Okay, so we're going to construct this Taylor polynomial and see where this comes into play. I'll move this over to the side. So this is what we're actually aiming towards. Sometimes they're not super complicated. Sometimes they're really, really nice. Sometimes they're really, really nice. Let me see if I can actually move this over first. F of x. So what do we first need to make a list of? What is f of x equal to? 1 minus x to the? Negative 1. So what's f prime of x, Papa Sam? Negative 1 minus x to the?
Negative 2.
Times? Chain rule.
Negative x.
No,
negative 1.
Negative 1.
Yeah.
So what is that equal to? 1 minus x to the?
Negative 2.
Negative 2. So what's f double prime of x?
Negative 2.
2, 1 minus x to the? Negative 3 times negative 1, which is what?
2, 1 minus x to the negative 3.
Do you agree with that?
Yeah.
So what's f triple prime going to be? Negative 3 times 2 times 1 minus x to the negative 4 times negative 1. But what do you end up with? 3 times 2 times, I'll put the 1 in there to be emphatic about it, to the negative 4. Do you agree with this?
Yeah.
So what is fn going to be on this one? What's fn going to be? N factorial 1 minus x to the?
Negative n.
Negative what? Like that, right? Or negative n minus 1. Do you agree with that generalization?
Sure.
Basically, this is a hunt for factorials. It really is. The factorial makes your life easier here. So that's what it is. So what do you need to do in each of these cases? You're doing it for x near 0. So what are you plugging in for x? You're plugging in 0. So what is f of 0? What's f of 0? 1. What's f prime of 0? Come on, kids. I'll line it up for you. So you can, I'll do it a different color. Okay. What's f of 0? 1.
Yes.
What's f prime of 0?
What's 1?
1. What's f double prime of 0? 2. What's f triple prime of 0? Well, 3 factorial, right? So this one right here, what is f n of 0? What's that going to be? N factorial. Do you agree with this? Are you okay so far? Okay, so let's go back and look at our definition, because if we ever lost, let's just look at our definition here. So we need to fill in the blanks. Let's play some fill in the blanks and see how we did. Maybe we got it right. Maybe we didn't. So we're going to degree n here. That's not what I wanted. I want to go to here. We're going to degree n. And it got that, but it's okay. So if we want to plug this in, what is f of 0 going to be? We already found out what f of 0. What is it? This number is what? 1. What was f prime? What was f prime of 0? What was it? 1 factorial. What was f double prime of 0? 2 factorial. What's f triple prime of 0? 3 factorial. So what do we end up with? We end up with this. We end up with 1 over 1 minus x is equal to approximately what? 1 plus 1 factorial x, right? And what's 1 factorial?
1.
So it's 1 factorial x plus 2 factorial over 2 factorial x squared plus what? 3 factorial over 3 factorial x cubed. Do you agree with this? Plus dot 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 all the way up to n factorial over n factorial x to the... Do a lot of things cancel?
Yes.
So what do we end up with? 1 over 1 minus x is equal to 1 plus x plus x cubed all the way up to x to the n. X to the n. Now you have to be really careful about this. Instead of writing 1, I like it when I say the answer. Instead of writing 1, you can write it as x to the 0. How do you prove that's true? And when is that true? Because is that true for all numbers?
The integral, if it's not just like a geometric series.
You would run the ratio test.
Okay, and that's
Mm-hmm. Yep. So here's the thing. What's the only thing that I added in right here? What's the only thing I added in? Just to make it more fun for you. A. Instead of centering it around 0, which would be a Maclaurin series, we can center it around anything we want in the domain. anything we want. So what's the only thing that changed so far? What's the only thing that changed? The a. Yeah, instead of 0, we have a. So this is that super general term right here. Here it is. That's the term you really need to remember right there. That's as general as it gets. Instead of 0 for a, it's anything you want it to be in the domain. Anything. Okay, so what are we going to do? You want to know what types of questions? You're going to do questions like this. You're going to do questions like this. It says construct the Taylor polynomial of degree 4 approximating f of x around 1. Around 1. There are the 3 pieces. So how many derivatives are you going to need to take? 4 of them. So that's the first thing that happens right here. Degree 4 means you do 4 derivatives. And then what do you do for each of those derivatives? What do you do for each of them? Plug in not 0, you plug in 1. This is important because can you plug in 0 to ln?
Oh, yeah.
You see what happens? It's not in the domain. So this is why you have to tack it to other places sometimes. You can't plug in 0. So do you get some nice integers here? Yeah, we let x equal 1. And then what do you end up with? You end up with, where's that 0? This 0 ends up right here. And where does this 1 end up right here? Where does that 1 end up? It's the coefficient right there. What's the next coefficient? Oh, look at that. There's the -1. That's this negative. Oh, there it is. So if you do this mechanically, this is going to be boring, 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 boring. What you do with it is where it's going to be fun. What you do with it is where it's going to be fun. Because you could, let's say you didn't have an ln function on your calculator to calculate ln. You could use this Taylor polynomial around 1 to estimate values of ln around 1. Does this kind of make sense? You'd be a little wrong, right? A little wrong. And then later we get to answer. So here's the general question I want you to answer. You ready? You want your general question? I want this.
Yes, we did.
What does this equal? Find that for me.